Hello again, and in this lecture we're going to solve an example for the equilibrium of a rigid body in 3 dimensions in order to see how we can apply the concepts that we've learned so far. Now, the biggest challenge with regard to 3D equilibrium questions is that often we'd have to solve for up to 6 unknowns, which obviously means that we have to solve 6 simultaneous equations. And this is, as you can easily imagine, is a difficult task often. And therefore we have to come up with a strategy to simplify our task somehow. The main goal when we solve 3D equilibrium questions is to, of course, eliminate as many unknowns as possible from the first equations of equilibrium. And you have to remember always that your best friends in this case are moment equations, because moment equations, if they're written judiciously, can help you get rid of many unknowns, maybe most of the unknowns that are not necessary in the first instance. So in order to do that, you'd have to first check if the question or the forces in the question that you deal with are in one of the configurations that we discussed in the previous lecture. So there were 3 special categories, and these were all forces concurrent at a point, all forces concurrent with a line, or all forces parallel. So if you recognize one of these situations, that's excellent really, because you will have to deal with fewer equations of equilibrium that you'd have to solve. So that would simplify your task already significantly. Now, the other important thing is the strategy for solving equations, for solving 3D equilibrium problems. You need to eliminate as many unknowns that you don't need as possible. So the most unknowns in general can be eliminated by writing moment equations about a line, because as you remember, forces cannot produce moments about a line if they intersect the line or if they're parallel to the line. And chances are that if you can write such an equation, you may eliminate a large number of unknowns. But often this is not possible, and if that's the case, you should see, and often you can, write moment equation about a point. And often this point is a ball and socket joint with 3 unknowns, so you can eliminate those unknowns or you can eliminate some other unknowns. But again, you should always start with writing moment equations either about a line, and if that's not possible, about a point. That would eliminate a large number of equations, so then you can solve the problem in a much easier fashion. Okay, so let's get down to business. So do an example, an actual example. What we have in this example are 2 steel beams. They have a cross section like I'm showing here. It resembles capital letter I. So therefore these beams are called I-beams because of the cross-sectional shape. And as you can see in this sketch, these 2 beams are joined together, like so. And they're welded, they're rigidly connected, such that they make a relative angle of 90 degrees with respect to each other. So this rigid assembly, which is obviously a rigid body, is suspended by 3 cables at A, B, and C. And the first beam on the left-hand side is 2 meters long. And then the beam on the right side is 3 meters long. with the cable at B being 1 meter away from the 90-degree joint. So these cables, the three cables at A, B, and C, hold the beams, hold the rigid body, the system, in place in such that everything is in the horizontal plane. So A, B, C, A, B, and C, and the two beams are horizontal. And also what is given is the mass of the beams, which is equal to 40 kilograms per meter, meaning that each meter of beam has a mass of 40 kilograms. In other words, the beam on the left-hand side is 2 meters long, so its mass is 80 kilograms, and the other beam is 3 meters long, and its mass is 120 kilograms. The question asks you to determine the force in the cables. So the first step, like in any question dealing with equilibrium, is to draw a free body diagram of the system. For this purpose, we will cut the cables at A, B, and C, and hence free the body from the environment. And this is the body that I drew. I've selected a system of coordinate axes, as you can see, X, Y, and Z. And by cutting the cables, we have now to represent the forces in the cables, which are tension forces, FA, FB, and FC. And the other forces that act on the system are the weights of the two beams, W1 and W2, acting at the center of each linear beam. So W1 will be 1 meter away from either end of the beam at left, and W2 will be 1.5 meters away from either left of this beam. All right, so this is the complete free body diagram of the system of beams of our rigid body, really. And now, if we look carefully at this diagram, we will recognize that all these forces acting on the rigid body are parallel. They are parallel to the z-axis. So hence we are in one of the special situations where we now need to write only 3 equations of equilibrium, because these parallel forces cannot rotate around the z-axis. So we will write moment equations around the x and y axes, and then also these forces that are parallel to the z-axis cannot translate along x and cannot translate along y, so hence we will only write the force summation along z. Now quickly, the weights of the beams, all we have to do is multiply the mass per meter by the length of the beams and by the acceleration of gravity, and we obtain these values. And now we have to write the equations of equilibrium. I selected point C to write the moments about point C and then around the y-axis. So from this equation I can solve for the force in the cable at A, which is 392 newtons, of course in tension. And then the second moment equation will also be around point C, but now around the x-axis, right? So both of these are moments about an axis, y and x respectively. So let's write this equation, FB, and now the weight, W2, equal 0. And from here, if we solve this equation, FB results as being 1472 newtons, of course in tension as well. And as I mentioned earlier, the third equation is a force summation equation along Z, along the vertical direction. We already know 2 unknowns, and these are F A and FB. So now all we have to do is solve for FC from this force summation equation. And if we do so, the result that we will obtain will be 98 newtons. Now, this is a good solution. It's a scalar solution, and it was simpler in this case because we dealt with parallel forces and we only had to write 3 equations of equilibrium. But very often, and in most cases really, in 3 dimensions it's very difficult to use a scalar approach. And hence this type of approach is discouraged in general. And what I'm going to present now is an alternate solution in which we're going to use the Cartesian vectors method, which is the one that you should generally use for this kind of questions. And for more complicated problems, the Cartesian vector solution would be more straightforward and easy to use than a scalar approach, which could be quite challenging in 3 dimensions, visualizing dimensions and forces in 3 dimensions. So I'm going to write the same equation, summation of moments about point C equals 0 in Cartesian vector format. So that means I would have to calculate the moments of each force with regard to point C. So I'm going to start first with weight W2. So this will be equal to the cross product between a position vector for W2 and the weight W2. The position vector will run from point C, as you can see in the diagram, to W2. And if we populate now the determinant and expand the determinant, we will end up with a value for this moment equal 1065.8 times I Newton meters. Then we go to the next force, which is the force at B. So the moment of the force at B at about point C equals to the position vector for the force at B times cross the force at B. And you can see how I show the position vectors on the free body diagram, which is very important in order for the free body diagram to be complete. If using this method, the position vectors must also be shown on the free body diagram, very importantly. So this moment will be equal to -2 times FBI Newton meters. Now we go to the next force, which is the weight W1. So the moment produced by W1 around C equals the position vector for W1 cross the force W1. And we populate the determinant and calculate this determinant, and we obtain 2354.4 I plus 784.8 J Newton meters. Don't forget about the units. Always remember the units. The next force is the force in the cable at A. So this one will be again equal to the position vector for the force in the cable A cross the force in the cable A. So let's show the position vector on the diagram, like so. And now you can see all the 4 position vectors. They all run from the point about which we sum the moments, which is C, to any point along the lines of action of the forces. In this case, the easiest point is actually the one contained in the XY plane. So we again populate the determinant, and this will result in -3FA I minus 2FA J Newton meters. There's of course one last force that may produce a moment, that is Fc, but since Fc goes through point C, the moment produced by Fc will be obviously equal to 0. So now that we've calculated all the moments, all we have to do in order to write the equation of equilibrium is to sum them up and set everything equal to 0. So this is what I'm doing right now. So we have 5 forces and 5 moments produced by these forces around point C. And now if we plug in the results and also group the terms in terms of I, j, and k in terms of the unit vectors. We get three expressions in I, j, k. Of course, the one in k is 0 because of the moment at c. And if we set these three terms equal to 0, in fact, we're writing moment equation summations about around point C about the x, y, and z axes. So in this case, again, there's no moment around the z axis, so we end up only with two equations for the coefficients of the term in I and coefficients of the term in j. And from these two simultaneous equations, we can solve for Fa, 392 k newtons, and Fb, 1472 k newtons. So the unit vector k indicates that these forces are along the z-axis. Now we have to write the other set of equations, which is the summation of forces, vectorial summation of forces equal to 0. And that means this. So all forces are parallel, run along the z-axis, so they all are in terms of k. And now again, if we plug in the numbers that we know already for these forces, the weights as well as Fa and Fb, we can solve for Fc, which is, of course, 98 k newtons. And at this point, we have solved again the problem using a different approach, the Cartesian vector approach, which is the one to use. This is the method that we will use in the future. So thank you very much for attending this lecture, and I will welcome you at the next one.